So we are going to start lecture series on Odyssey of Physics. So this lecture series we started last year. So this is the 6th seminar in this lecture series and the first from this year. And basically the aim of this lecture series is to invite eminent scientists across India and abroad working in different areas of physics and listen to them. Basically, it's an opportunity to listen to them directly on their works, on their future research plans, and directly interact with them. So far, we have invited, as I said, 5 people already in the last year, starting from Professor Puru Jena from Virginia Commonwealth University in USA, and then Professor Patnaik from JNU, and Professor T. Narayana Rao from Hyderabad University, Professor Kalabaran Maiti from TIFR Mumbai, and lastly, Professor M.S.R. Rao from IIT Madras. So we are very happy to have Professor Parankama Sen from University of Calcutta with us today to give the 6th lecture in this lecture series. So before we start, let me tell you technical thing that this talk is for 50 minutes and then 10 to 15 minutes question answer session. And this is, as you can see, this is recorded and also will be live telecasted in YouTube. For participants, there is an option to ask your questions to the Q&A box below. You can see, you can type your question. We will take up the questions at the end of the talk. Or also, if there are a pressing question, you can unmute and we can take up such questions also. With that, maybe I would like to request Professor Ranjit, our HOD, to say a few words about our department, research activities, and the future plan. Professor Thapa.
Yeah, thank you, Amit, Dr. Amit. So it was really nice to have an eminent scientist and professor, Professor Sen from University of Calcutta. Welcome you, madam. And this is our 6th version, and we are doing in bi-monthly or monthly whenever we have a little bit a good time for doing such activity. So I will just tell something about our department. So actually we as a university is a very young age university, only 4.5 years old. And our department is around 4.5 years old, but we started first BSc Physics in 2018, of course in a less number, and now we are also having PhD students, and also from this year we are starting MSc Physics. And BSc Physics already we started with a 4-year program, which is BSc Research. So that means the 4th year they will do the research program, like research degree will be there. And we have currently 31 PhD students in our department. And we have 11 faculty members from particularly we concentrating on the 4 group. One is particularly advanced material and device group. Another one is computational and statistical physics group. Another one is high energy and particle physics group, and another one is the last one is laser and optics group. So this is the main group which we are concentrating in our department. And in last 3 years we have got 11 funded project with a total outlay of 4.5 crores. And our faculty member, PhD students and BSc students published 120 publication in last 3 years, where 80% are in Q1 journal, and out of which 7 in Nature Index journal. So this is really a very important steps towards the research-centric department and university. And also our faculty member have published 6 patents in the last 2 years. So with this, this was a short introduction about our department, and we want a very close association with you all. so that we can grow more faster and we can expose ourselves in more different domain also. With this, thank you, Amit. Thank you.
Professor Taba, may I now request Dr. Soumajyoti Biswas to introduce the speaker and start the seminar.
Thank you, Amit. It's a great pleasure to introduce Professor Aurangama Sen, of course, whom I started interacting as a teacher in our master's days and then as a long-time collaborator. Professor Sen did her PhD from Shah Institute of Nuclear Physics in '93. Then he joined as a research associate at Jawaharlal Nehru University. And after doing postdoc in University of Cologne, she joined the University of Calcutta in the year 2000. And from 2008 onwards, she's a professor there. Her research interests broadly is on statistical physics of phase transition, critical phenomena in magnetic systems, in networks, dynamical phenomena in complex systems, sociophysics, among other things, and quantum phenomena as well. Her work on this small world properties of Indian railway network is one of the very highest cited work from the department. She has been a regular associate of ICTP, International Center for Theoretical Physics, till 2010. She has also been an IMSc, that is Institute of Mathematical Science associate, since 2011 to 14, I think. So today she will be talking about interacting particle with annihilation, which I think spans several of these fields that I mentioned, this non-equilibrium critical phenomena and complex processes in network systems. So yes, over to you, Professor Sen.
Thank you so much for a nice kind introduction. And of course, thank you very much for the invitation. And I'm also happy to know about the progress of your department from your HOD. And I wish that you prosper more and more in future. Okay, so only one thing, Shombo, I was not a professor before 2012. However, those things don't matter really. Anyway, but that's a fact which should be corrected. Not since 2008, but 2012. Okay. Right. So, as Shomo said, that of course, this work, the name actually, the title of the talk sounds too general, but it doesn't really cover so much as Shomo said. But anyway, we have done quite a few things in this area, and I thought that I would share that with you. Okay, so I have shortened the title a little bit. I think that non-equilibrium and all those things I've removed and just titled it as Interacting Particle Systems with Annihilation. The first 20, maybe 15 minutes or so will be basically review types, and the experts in the audience may take a short nap, and because that is those stuff are all there in the textbooks as well. So let me begin by thanking my collaborators. Reshmi Rai, I think she is in the audience. Pratik Mollik. Reshmi is in the final year of her PhD and working in CU. Pratik graduated from CU and he is now a postdoctoral fellow in France. Shoham actually graduated long time back and he is a faculty now at University of Guadalajara in Mexico. And of course, the last but not the least, Purushottam Rai, retired professor in IMSc Chennai. These works have been supported by CSIR and ACRB projects. Maybe it was called DST at that time when we started this thing, but anyway, doesn't matter once again. Okay, so these interacting particle systems have some very basic properties. First of all, we take a system of many particles in which the states of the particles are changing at every time step. Time steps can be discrete or continuous, and there will be some prescriptions, some rules, which is going to govern the whole dynamics. Usually, we take a stochastic dynamics that is more interesting. One can also think of deterministic things. Stochastic dynamics means that there is a randomness associated with the dynamical process. And also usually we have a Markov process. In this particular talk, I am going to restrict to Markov processes only, in which the state at the present state is determined fully by the state at the next step is determined fully by the present state of the system. But of course, there are some nuances, like there can be in a numerical simulation, there can be different types of updating rules, and that also we are going to address. But basically, it is a Markov process. So a very basic or a very prototype model of interacting particles is the voter model. Please remember, it has got nothing to do with votes, and many of you are familiar with it. In the simplest possible voter model, there are two states possible, say call it A and B. And these states change upon interactions. An agent changes to the state of a randomly chosen neighbor if the states are different. If same, there is no change. So essentially, this model is designed in such a way that the agents just try to copy the states of the others. And this model therefore mimics the process of things going viral, because everyone is copying from what the other person is doing. So ultimately there will be one some style or some fashion or some news which is going to become viral. So let me just explain the dynamics in a few more words. For example, suppose you the one agent has opinion A. The updated opinion is given by the following interactions. So in this case, I have highlighted the opinion of the agent who is randomly chosen. So if the randomly chosen agent has opinion A, then the resultant opinion is A for both of them. If the highlighted or the randomly chosen agent has opinion B, then we have the resultant opinion is that both of them become B. And similarly for the other opinion, that is if you start with an agent with opinion B, it is basically the same process. So this I can call or term a single species system, because though there are two types of opinions, but there is a single species. The species are the same. They don't have any classification. Only that the states are binary. So one of the most extensively studied systems in interacting particle system is called the reaction diffusion system. So basically it was developed to understand how the chemical reactions take place. So from that we have this reaction term. And as I said, that it represents the time evolution of densities of chemically reacting species whose long time behavior is dominated by diffusion. So for example, we can have a reaction like A plus B going to C plus D, etc. And they will have certain rates associated with this reaction. And in this process, what will happen? We'll lose some A, we'll lose some B, and we'll gain some C and gain some D. But and there will be other reactions also involved, so that it will be a completely dynamic process in which these the density of the species will increase or decrease depending on the type of reaction we have. The result is there will be some exotic pattern formation. These are taken from the internet, and this may also be thought of one model in which you can generate different patterns. So if I now want to generalize this thing, not limited to chemical reactions only, then I can use a reaction diffusion model for systems of diffusing particles representing molecules, biological or chemical entities we have already discussed, market commodities, opinions, etc. So two basic things are involved. One is the interaction and the particle dynamics. And these type of systems can be studied using many type of methods. Of course, there are analytical methods. You set up some time evolution equations, master equation approach, which also is nothing but a time, ultimately you set up some rate equations, then numerical simulations or agent-based models. Also, sometimes this time evolution equations, they cannot be solved exactly. So ultimately you take resort to numerical methods. The most important issue, of course, is how the concentration of the species are influenced by the motion of the reactants. Okay. But of course, there are many other issues involved, which we are going to discuss as we proceed. And as I already told you, that the overall concentration may change. And when in the chemical reaction. When we talk in terms of general systems, then we say that the concentration may change due to annihilation or branching processes. Since in this talk, I'm going to limit myself to annihilation processes, I am going to focus on that. So again, going back to a chemical reaction, suppose you have A plus B going to C, where C is an inert entity. That means C doesn't react anymore. Then effectively you have two reactant particles, they are annihilated when they meet, or they are within the so-called reaction radius. Okay. And symbolically, we write it as a one species model. We can write it as a model, and the simplest possible model can be for a one species system, that is A plus A going to 0 or null, because that result is an inert quantity or entity. We just keep it as nothing. Okay, because we have lost both the reactants. Now, these types of equations can now be generalized and can be thought, you can think of many types of reactions like this. For example, if you have a two species case in which you imagine that there's one species which is being attacked by the other species or eaten up by the other species. So that we call it the predator-prey model. In this case, A is the prey and B is the predator. And I'm just showing you how differential equations can be set up to study this system. So there are many such models, and one of the famous models is the Lotka-Volterra model, in which the population densities for A and B follow these equations. There's no need to go into the details. This is just an example. Here you see that the more B species are there, A will be eaten up. So this is a loss term and this is a gain term. This is kind of a Barth term. For B species, if they cannot, if there is no A, so this term is not there, they are going to die. So therefore, there's a minus rho B here, and here you have a positive term because they will grow or they will gain in number if they can eat up A species. So it depends on the density of A. So there can be, as I said, many such models. You can have a model in which A and B annihilate each other, that is A annihilates A also, etc. Or there can be reinforcement models, there can be symbiotic models, etc. And we are not going into those details right now. Okay. So I will just discuss another example of population dynamics. See, these models also go under the name of models of population dynamics. I'm discussing it because this model, although it is very, very old, now it has become quite famous and popular. It is they are the prototype models for infectious disease spreading, and these models have been now modified and studied a lot in the context of the pandemic. But the basic models which were proposed some 100 years ago, they contain, they are of two types. That is, one is the SIS model, which contains three types of population densities: susceptible, infected, and susceptible. And SIR, in which you have a removed population also. That may include the population which have died after contracting the disease, or they are no longer infected. So in SIR, you can be infected only once, and once you are infected, you are removed from the system, either by death or just because you have attained immunity. So once again, you see that you can set up some differential equations, and there are some kind of annihilation and reinforcement terms for SIS models. Similarly, for SIR models, you have annihilation for the susceptibles. There is no reinforcement here, and there are other equations. We need not go into the details of this. This is just to motivate you how these type of models are relevant for actual use or actually studied in which context and so on. So there can be some other phenomena like this, like the process of rumor spreading, birth, death processes, etc. So for each of these processes, you can have some similar equations, setting up differential equations. Basically, they are what we call mean field equations, because we are only taking the densities in this thing, and no fluctuations or no individual pattern is going to be followed here. So let us think of a single species model with annihilations. In general, we can write that there are k number of A-type species and only one type of species here. So k number of that, they have a reaction, and that leads to L number of species ultimately. So because we are only addressing the question of annihilation, we will take L to be less than K. And the simplest possible cases are L equal to 2 and K equal to 0, which is the case already discussed, that is A plus A going to 0, that is complete annihilation. We can also have, oops, sorry, this should be just opposite. This should be K equal to 2, L equal to 0, and this should be K equal to 2 and L equal to 1. Just take it the other way around. I'm sorry for this mistake. Okay, so you have two species to begin with, and you lose one after the reaction. So this is called coalescence. So as if these two species have joined together and become one. Okay. Now one can write down very simple mean field type of differential equations for these diffusing particles with annihilation. So you have the diffusion equation here, del rho del T, that is the change in the density is given by the diffusion term. And then there is minus K rho square because there is annihilation when the two particles or the two densities are reacting. So you have a minus K rho square. That part will be proportional to rho square. And if the reactants are perfectly mixed, then the system becomes homogeneous. And then asymptotically, you can expect that the first term on the right hand side will not contribute because it is there is no fluctuation in space. And so finally, you get the result that rho T is proportional to T inverse. Of course, true asymptotic behavior will depend on the dimension. So next, we are going to discuss some known properties, especially in one dimension, and then move over. So as I told you, we'll discuss some known results. So for the perfectly mixed model, as I already mentioned, that rho T will be proportional to T inverse, but it can be shown by several methods. Most simple is the dimensional analysis, which shows that it is not correct below D equal to 2. That is D equal to 1 or 2, it is not going to be correct. But above that, it is okay. So specifically, if we take the one-dimensional case, the exact result is that rho T is proportional to T to the power minus half. Now, these reacting particles which we are talking about, since we are assuming that they are undergoing diffusion and of course the reaction, then we can regard these diffusing particles to be random walkers. Okay. So these random walkers have this property that they diffuse following diffusion equation as usual, and they also annihilate each other as they move when they collide with one another. Now, another type of system which can be conceived where the particles move ballistically and annihilate upon colliding. It is called ballistic annihilation model. I am discussing this one but in particular because this will be relevant for our future discussions. So if you think of the simplest model in one dimension, then the particles are moving ballistically. That is just, they are just going linearly, either to the left or right with constant velocity. So in the simplest model, you allow only two velocities, either v or minus v. And this model is also quite old, but there is a recent article which you can read if you are interested. It is a review article. And if you want to study it more deeply, then you should be able to appreciate that it is equivalent to a 3-species cyclic predator-prey model, which I have written here. And the 2-species cyclic model is nothing but the Wotan model, and so on. Okay. So right now we have two models which we have discussed, and we'll see that how they differ and how they are similar. See, in this ballistic annihilation model, although the particles are executing a different type of motion, they are moving ballistically, not diffusing. They are not diffusive particles. Still, you see the particle density decays as T to the power minus half. So the particle density decays in the same manner in the A plus A going to 0 and in the ballistic model. Now, in statistical physics, more often than not, we have this advantage of mapping one system to another, and then it becomes very easy because one system may look quite difficult to tackle, but if you map it into another familiar system, then you'll see that it is more easy to handle. And therefore, we are going to just discuss this mapping of one system to another. In this case, we have a mapping of the dynamical spin systems to these type of reaction diffusion system. And it also helps us to So it also helps us to understand why these models are so important, because you see that they can be connected to other models of importance in statistical physics, in physics in general, actually. And in fact, outside physics also, reaction diffusion systems are relevant to many other systems outside the realm of physics. So this Ising model also is almost actually a century-old model now, and proposed in 1920 and ultimately solved, and the published paper was in 1925. And it was proposed initially to understand how a ferromagnetic to a paramagnetic phase transition takes place in order to understand Pierre Curie's experimental results. But as you know, in time, it has become a very important model, and it can actually, it is useful for many other types of phenomena apart from spin systems. So we are not going to go to a detailed discussion on Ising model, but we'll need to mention what is the Hamiltonian. The Hamiltonian is simple. It looks by minus j sum over si sj. In this talk, I will only take nearest neighbor interactions and j to be positive. SIs are spin variables which are plus minus, which can take values plus minus 1. We all know that there is a phase transition which occurs at a non-zero temperature Tc in dimensions greater than 1. In the classical model, there is no intrinsic dynamics for the Ising model. Why? It is easy to understand, because you see in the Hamiltonian, there is no non-commutative term, because basically we have not mentioned which component is there, but only one component is present, and therefore there is no question of any non-commutivity. So essentially, we know that if I regard the spins as operators, then they have to, then we can take the Heisenberg equation of motion. But since the Hamiltonian commutes with the Sz, then there is no intrinsic dynamics of Sz. However, one can think of a different kind of dynamics. Sometimes it's called kinetics in this case, even though it's a classical system with no intrinsic dynamics. One can think of the system to be taken far away from equilibrium and then allow the system to relax and see how it goes to the equilibrium state. This is also an important aspect in some practical cases, and therefore this is also an important study. Now, in case of the spin models, what we expect is that if we are allowing the system to relax below the critical temperature, we know there is an order in the system. So if we start with a completely, say, random configuration, which corresponds to a very high temperature, maybe T going to infinity for completely disordered state, and then if we allow this, if we suddenly make this temperature go to a lower one below Tc, then we expect that the system will tend to order. But of course, it will not happen instantaneously. It is going to take some time, and because each spin has to do something to go to, and cooperatively, some emergent behavior will arrive, and that is the ordered phenomenon. Order will appear in the system, and that is going to take some time. And of course, in a finite system, we'll always get a all up or all down state. But the interesting point is how it reaches this state. And this has been an age-old question in statistical physics. So now when I ask the question that how it reaches the equilibrium state, or whatever state it finally reaches, then we have to think of some kind of dynamical rule, okay, and to study the system. So that is done by, first of all, setting up a master equation. Once again, I'm telling you that experts in the audience, you can just take rest, because these are basic textbook materials. Only since Shobo told me that there will be a lot of students, therefore I'm just going to these steps. So you set up a master equation to find out how the probability of a configuration is changing. There will be some gain terms and there will be some loss terms. Okay, and we have to take into account how the transition is taking place. So in this particular case, you see that there will be a loss when the A type of configuration is going to B type of configuration. So this transition rate is from A to B, and that is a loss term. And it can go to many types of other configurations. So we sum up over B. Similarly, we can arrive at A from many other configurations B, and the transition rate is WBA, that is from B to A, you have a transition here. Now, at equilibrium, when the left-hand side is 0, you have this quantity to be, you demand that this quantity is equal to 0. This is called the principle of detailed balance. And if you, and you know that this equilibrium probability is given by the Boltzmann expression, which is e to the power minus e by kt. And then all you can have is a ratio of these transition rates. So basically, in order to study the system, you need to know the transition rates. And how do you choose them? See, because you only get a ratio, then there is no unique choice. So you can have many choices. Only thing is that you have to obey the detailed balance condition. So if we think of, as I said, we can think of many such choices, but we'll discuss only the Glauber dynamics at 0 temperature, which we have used here. So the Glauber dynamics is very simple. At temperature T equal to 0, at each step, what you do is you think that only one spin is flipped. You simply calculate the change in energy. If the energy decreases, then you accept that move, that is, you flip that spin. If it increases the energy, you don't do anything. And if the energy remains the same by flipping, then you flip with probability half. So schematically, it is like this. Suppose at time t, this is the configuration, and you have chosen this one, and just checking whether you should flip it or not. You see that if you flip it, then this configuration is energetically more favorable. So you accept this. On the other hand, when you have a red and a blue, these represent the two different states, then you can flip it with probability half. So the final state at t plus 1 is either this or that. If there is any question, you can ask me. Unfortunately, I cannot see the chat box. So if there's any question in the chat box, the organizers can please just...
Beyond the question, there was actually one question.
Okay, actually, I can't see it for some reason. Can you tell me?
It says, why the annihilation term proportional to rho square?
Yeah, because you need two particles to annihilate, isn't it? So two density square, essentially.
Yeah.
I hope
there was a question by Akif Molla.
Yeah,
okay. that was the only question that is there.
Okay.
Participants can please type in the questions if they want, or later on as well.
Yeah. Okay, but just tell me and stop me and
sure.
tell me, because for some reason I cannot see the chat box. Okay. So as I told you, the question is, how does the system reach the ordered state? And schematically, you can have a picture like this. I have shown a two-dimensional picture in which, starting we had a kind of completely disordered state, and as time progresses, MCA stands for Monte Carlo steps. So as time Monte Carlo steps progresses, we can see that order is building up. But what we see here is that we have some domains building up. These two colors represent the two states of the spins. So we can see that there are larger and larger patches of white and this chocolate color appearing in the system. And in the last one, we see that there are even larger patches coming up. And if we go to even further steps, then we'll see that ideally we'll be left with one patch only, but that doesn't always happen in 2 dimensions. And that's a different issue, which we are not going to address right now. Okay, but basically what I'm trying to say is that there will be something called the domain growth. So there will be domains of like spins which start growing from small sizes to larger sizes. And this will happen in all systems. Even if it is an infinite system, it will happen. Only for finite systems, we'll end up with one type of domain only. For infinite systems, both will grow in time. And typically, we have this type of behavior that the domain size dt increases with time in this manner, d to the power eta. So d is roughly a dimension, the dimension of the domain, or one can say it's the radius of the domain, and eta is called the domain growth exponent. So there are some other interesting features also related to the 0 temperature quench. It is also called quenching. So there is something called persistence behavior. It is quantified by the probability pt, that a spin does not flip or change sign till time t. And PT shows a Pauli decay in many systems, Ising systems, of course. Pt goes as t to the power minus theta. Theta is an independent exponent. It is not related to any other static or dynamic exponent. And although eta, we have seen there is universal, that is, actually this line should be before this. Domain growth exponent for Ising model is half for all dimensions, but persistence exponent is non-universal and dimension dependent. Now there is also another feature. While coarsening, as I told you, domains of different sizes will exist at any time. The distribution of the domain sizes can also be exactly obtained in one dimension for the Ising model. And for large sizes, the behavior is the distribution of domain sizes decays exponentially. This is also a known result. Now I am going to tell you how this mapping between the Ising model kinetics and the reaction diffusion system takes place. So you imagine this is only true for one dimension. Okay. So in one dimension, suppose you have a simple picture like this. As I told you, that domains will start growing in the quenching process. So here you have this domain here, this domain, and so on. You can easily check this, that the spins which are deep inside the domain, they are not going to flip. Only the spins which are close to the so-called domain boundaries, they are liable to flip, and they will flip with probability half. So there can be a situation in which from this configuration, I arrive at this configuration in the next time step. So you see that here I have drawn something. This is a kind of a pseudo particle. It is a domain boundary. Now this entire dynamics can be thought of as the movement of this domain boundary here to this position. And if this spin has not flipped, but this spin had flipped, this is also liable to spin with probability half. This domain boundary would have moved one position here and would have gone here. So effectively, we have the motion of some so-called pseudo particles which will perform random walk because it is going to the left or the right with equal probability. Okay, so whenever we have this type of a situation. Now we can also have another situation in this kinetic Ising model. That is, if you have a single spin of opposite sign sandwiched between these two. In this case, you have two domain balls, which I can say they are nearest neighbors. Now this spin here is bound to flip because flipping this will decrease the energy. So this will always flip so that these two domain balls will vanish, and I can regard this to be a reaction of the domain balls such that they have vanished upon collision or meeting. So now you see why I am claiming that this whole thing can be represented by the same equation which we had written before, that is A plus A goes to 0. So for the Ising model, we can have an equivalent random walk picture. This is time and this is space. So we have here one domain, say, of negative spins or say down spins. These are up spins, these are down spins again. So these are the boundaries which are now moving in time like this. These two have met and already got annihilated. So therefore, you have an interesting mapping is there. Now we have to also understand the mapping of the different quantities. The phenomena we have already mapped. So the particles or walkers remaining in the system is now equivalent to the number of domain balls. And this whole thing is proportional to the average, and this is proportional to the average domain size in one dimension. And the persistence property for the Ising model, now I can attach it to the system of random walkers in this sense that the fraction of unvisited sites till time t is nothing but the persistence probability. So unvisited means that none of the random, we have a system of random walkers, so none of the random walker has actually visited that particular site. So we are thinking the random walkers to be on a lattice, one-dimensional lattice. Now we also have a domain size in the one dimension, and this will basically correspond to the interval or gap between the two walkers. So here we have a domain of size 3, and you can see that this is the gap between two domain balls. So this domain size corresponds to the interval or gap between the two walkers. So because this is also a well-studied quantity, one can also calculate this quantity, interval or gap between the walkers. Now we go back to the ballistic annihilation model. ballistic annihilation model, we had seen that rho was decaying in the same manner, but now we mentioned what is the different thing here. Persistence exponent theta is equal to 1 here, which is different from the random walk model. But in the random walk model, it corresponds to the Ising model in one dimension. So it is 3/8, the known value. Okay. So you see that basically what I'm trying to emphasize is that these exponents are to be estimated in order to identify to which dynamical class a particular system belongs to. So it is important to know. So ballistic annihilation and A plus A going to 0 are not the same, although they have the same manner of decay for the particle density, but persistence exponent is different for them. So they belong to two different classes. So we have another mapping here, which is the mapping of the coalescing random walkers, but I think I have already taken up too much time here. So I'll just briefly mention that we have something called the Potts model also, which is a spin model, and that can be mapped to the A plus A going to A model. Okay, so we are not going through the details because there is not much time left. So I would just like to mention a reference here. The general reference is a kinetic view of statistical physics. It's a book in which you can get all this information. So let me go to the second part of my talk, which is where I am going to discuss a model which we have been studying for maybe, yes, of course, more than 1 decade. And that is a model which actually should not be called a reaction diffusion model, but we somehow generalize it and we can say that it is a reaction diffusion model. But actually there's no diffusion happening here. You'll presently see why. You see, in the A plus A going to 0 model, we had seen equal probability of going to the left or the right for the walker. Okay. Now we consider a modification. So just look at this figure. So these field circles represent the walkers on this lattice. And now, suppose I pick up this particular walker, then as you know that there is only 2 possibilities going to left or right, but now the probabilities are not exactly half. The probabilities are 0.5 minus epsilon and 0.5 plus epsilon. 0.5 plus epsilon is the probability to move towards the nearest neighbor. So in this case, you see this one is nearer to it. So it will move towards this one with a probability 0.5 plus epsilon and move towards the other one with the probability 1 minus this thing. Now, if the 2 nearest neighbors are at the same distance, then it can move either way with equal probability. But otherwise, it is a kind of, there is a probability associated which is characterized by this epsilon. Now, you can easily see what is the limiting values. So, if the epsilon equal to 0 limit is of course nothing but the diffusive case. Now, epsilon equal to 0.5 is a quasi-deterministic case, and actually one can show that this annihilating random, also we have annihilation associated with this. So the same rule holds here that if 2 walkers meet or collide, they are going to annihilate each other. So this annihilating random walk system with the bias has a 1-to-1 correspondence to a spin model when epsilon equal to 0.5. So this was an old model which we had conceived in 2009 with Shoham, Bishar. Actually, Shoham worked a lot on this model. And in this model, you see that it's just a spin version. Here, what you have is that you have the spins, and of course, there are different domains here. And a spin can, at the domain boundary, can only flip. Okay. And how will it flip? It will look at both sides, and whichever is the larger domain, it is going to larger domain means larger in size, it is going to follow that opinion, that spin. So because you see here, there are, this domain is only size 2, whereas this is of size 5, so it is going to flip. So in the next time step, you find this kind of a configuration. And again, equivalently, you have this random walker here and a random walker here. Sorry, not random walker, we should just say a walker here. So these 2 walkers, this walker has now moved 1 step towards its nearer neighbor. So this and the other model which I just talked about, they have this 1-to-1 correspondence. And of course, the other thing holds good, that for annihilation, you need to have these two these two walkers come close, and this spin is going to be always flipped, because this is sandwiched between two same domains. So you have this to be the final state, and in this case A1 and A2 have vanished. Okay. So when we started looking at this model, we were primarily interested in the bulk properties, that is eta and theta. And I'm sorry if there's a change in notation now. Eta is equal to, say, 1 by z. So we have evaluated what is the value of z. And z is sometimes called the dynamical exponent. And theta, of course, is the persistence exponent. Now, in order to analyze the persistence probability, one can use a scaling form in this form. The advantage here is that you have theta and z both appearing here. So if you can do data analysis using this type of scaling form, and if you do get a collapse of the scaled data, then you can know both theta and z. So that will be a double check for the value of z. So we have done exactly that. This was a okay. So order parameter we don't need here much. So what we had measured here is the number of domains, which is also proportional to the number of particles remaining in the system, and it showed behavior like this, that is T inverse. Okay, and this is the persistence probability which we plotted with this scaling in mind, and we see a data collapse when we plotted the data for different system sizes. And the exponents which we obtained was z was equal to 1 and theta equal to 0.235, and this was obtained for epsilon equal to 0.5. So epsilon equal to 0.5 is almost a deterministic case. This is the first problem which we did. So we had kept epsilon equal to 0.5 and obtained these exponents. And now you can see why we were so excited with this model, because these exponents neither match with the Ising model nor with the ballistic annihilation model, and also not with the other well-known dynamical models which you will find in that book which I referred to. So our claim was that it is a new universality class as far as dynamics is concerned, ordering dynamics or coercioning dynamics is concerned. And later on, numerical results also indicated that the exponents are independent of epsilon. So that's a good news, because we are always interested when there is a universality, and this was done later on, and this was the results which we had found. Okay. So as I told you that there is also another interesting quantity, that is the domain sizes, right? So that we had actually done some years later on, and using a method, an approximation method, which is called the independent interval approximation. So as I already told you, the domains correspond to interval between two particles in the walk picture. And in the independent interval approximation, which has been used by many people before us, one assumes that the intervals are uncorrelated. So that is why the independent word appears. Of course, there cannot be completely uncorrelated, but this is an approximation and it works well. Okay, and you can actually obtain several results like the scaling behavior of the particle density and so on, etc. So what you do is, I've just introduced you to some new notations. So if you think that if you take nk to be the number of intervals of size k in a system of size L, then we are interested in this quantity pk, which is basically the number of intervals of size k per site. And then it is possible to set up a time evolution equation for the IIE. It's a very complicated equation when epsilon is non-zero, and I've not written it down because it's very difficult to explain all the terms here. So I'll just quote the results. So basically there are two things which we have to keep in mind. Sum over pk is just the total number of interfaces, which is equivalent to the total number of surviving particles. And also this there is a normalization, that is sum over k pk equal to 1. And you can easily understand that how we can get the average domain size also by calculating k squared pk sum over that. And then of course normalize it by sum over k pk. So there is an exact result for the Ising model where which has shown that pk has an exponential decay for a plus a going to 0 systems. Now this result, as well as the exponent eta, can be reproduced from using IIA, but there is a subtle subtlety here, because the exact form is not exact form of the decay, exponential decay is not found, but otherwise qualitatively everything is found, and quantitatively the behavior of rho is also obtained using IIA. Now I use one more equation here, that it is expected that pk will obey this scaling form such that the average value of k, that is the average domain size, remember, is proportional to t to the power eta, and the particle density is just inverse of this in the one-dimensional system, so this will be proportional to t to the power minus eta. So as I told you, it gives correct estimates of exponents and scaling functions for epsilon equal to 0. Now the results what we got, I'm just showing you some pictorial, some diagrams, and here what we had done, we had actually set up this differential equation, true, but we had to solve it numerically, and when we did that, we found nice scaling collapses for the different data for taken at different time, and then we had this z, which is equal to 1 by eta. We had to use a value of z in order to get this collapse, the best fit, the best value of z to get this collapse, and we obtained z equal to very close to 1, as already we had obtained from the other method, that is basically Monte Carlo method, z equal to 1.03. These are shown for two different values of epsilon, 0.1 and 0.5, and this is the full result for different epsilon values. We get these values of z. You can see if we are very, very close to epsilon equal to 0, then we see actually what is happening, there's a jump. For epsilon equal to 0, we know that the exponent z is equal to 2 corresponding to eta equal to half. And the moment we introduce an epsilon, it is going to 1. But of course, numerically, it is very difficult to get a jump like this. So we get something like this here, a very sharp fall close to epsilon equal to 0, because this is a kind of, there's a kind of phase transition happening here. And then we find the results are pretty close to 1, between 1 and 1.2, not exactly 1, but we claim that it is consistent with the previous results, that z is equal to 1. We also did this thing numerically to obtain pk, and we obtained again these collapses, and because in this system the particle decay is very fast, then it is very difficult to go to large times, and therefore we had to restrict to small times here. And already you can see that for the maximum time it is going outside the scaling regime, so the scaling regime is limited to this kind of a region. So we found that z equal to 1.1 and z equal to 1 again, one can get these values to get these collapses. And also we obtained this behavior of the scaling function from these also. This you can see these are log linear plots. So it is an exponential variation. So we see that the Ising model and this model, they both of them have this exponential behavior of the this function, this scale function, pk. And although the value of alpha differs from in the numerical method and the IIA, we get a difference, but that is also true for the epsilon equal to 0 model. So it is not surprising that we get a different value for this thing. Okay. So after all these works, there was a long gap, and then Reshmi joined, and then these works were again kind of, we had again revisited this model, and these works therefore are much more recent compared to the ones which I already discussed. So now, after getting all these bulk properties, the question that naturally arises that how do the walkers behave in the microscopic level? So we have obtained that z equal to 1, which implies that x, the length scales are going as t, which means it is a ballistic type of thing. But the walkers individually cannot be like ballistic annihilators, because we know that ballistic annihilators have different exponents, right? And also we know that they cannot be ballistic because there are occasional change in direction of motion due to annihilation of neighboring particles. So that is why, of course, the exponents didn't match. So we have computed quite a few things here. So one is the probability distribution, the probability of finding a particle at a distance x from its origin at time t, probability of direction change at any time t, and distribution of time interval tau spent in the same direction. For epsilon equal to 0, when the motion is purely diffusive, we all know that this probability distribution is Gaussian. Scaling variable is x by t to the power half. But we see that the moment we have epsilon not equal to 0, the behavior of this probability distribution changes drastically. Can anyone tell me how much time I have left? But I think I started a bit late, not at 3 o'clock, definitely. So how much time do I have?
Yeah, about 10 minutes, I think.
Okay.
10,
So maybe
10.
I'll take 5 more minutes. Huh?
Yeah, 10
Okay,
minutes.
so we also found that x by epsilon t actually emerges as the scaling variable for all epsilon. So that is why also epsilon did not actually matter in the scaling, which we had obtained earlier by numerical simulations. So these are the distribution of the positions of the particles. You see there, it looks like this, and if you increase the time, then you see these are early time behavior and this is a late time behavior. You can see as if there are two delta functions emerging out of this, and this is something, and we actually tried to fit some function, but we don't have actually any kind of analytical theory, but this is just by fitting the data. Then the next point is probability of direction change, that is measured by calculating the fraction of walkers that change direction at direction of motion at time t. Epsilon equal to 0, we know that it is a constant, that is a half. Now here was a surprise. Here we found that for epsilon equal to 0.5 and epsilon equal to epsilon not equal to 0.5 gave quite different results. Epsilon equal to 0.5, we have a power law tail like this, st going as t inverse till large times. Ultimately, these are finite size effects, or we have gone outside the scaling regime. But we found that for other epsilon values, it has attained a constant, kind of. So we made some more analysis of these data and found that we can obtain a data collapse by plotting STT against T epsilon C minus epsilon. And this gives us two regimes. One regime is almost like a constant up to roughly the value 1, actually less than 1 for this variable. And then for larger values of these variables beyond 1, it shows a linear behavior. So these points are summarized in this block, and then we claim that there is a time scale T star below which we have a power law, and beyond which we have saturation value of ST. Of course, this is not true for 0.5. We are just away from 0.5, very close to this point, 0.5, and then we get all this kind of interesting behavior. So what is happening here, therefore? You see, when we get the saturation region, that means that particles are basically manifesting individual behavior. That is, if had there been no reaction, they would have been like diffusive particles, maybe with a bias, and that is why the value of the ST is less. But otherwise, they are behaving like independent particles. So, but beyond that time scale, they are still behaving like correlated particles, because in that regime, annihilation is taking a significant role. So we go over to an annihilation dominated region, to an individual, to a diffusive type of diffusion dominated region, or in other words, there is a crossover between a correlated to an individual motion. And this T star acts as a time scale which shows a divergence at epsilon C. And from that, we can claim that epsilon C is a kind of a dynamical critical point, because we have this kind of a critical slowing down happening here. Okay, so the same results, same kind of behavior was confirmed when we also took the distribution of the time intervals. Again, we have a crossover. I'm not going through the details because we don't have much time, it seems. So we find that for epsilon equal to 0.5, there's a different behavior, but for other epsilon values, we have more or less an exponential variation up to a time scale. And again, that time scale is epsilon C minus epsilon to the power minus 1. And not time scale, actually, this interval time scale here, and so on. So we just say that a similar crossover behavior is confirmed from this one also, and the same type of behavior is also obtained for A plus A to A, the coalescing walk, and we do expect that they will be similar because one can show that they also have other exponents to be same. Okay. So one can actually have make some estimates of the values which we get, the power law behavior of ST and DT, not exactly analytically, but based on the previous numerical results, one can derive that ST will be proportional to T inverse, and this D will be proportional to tau to the power -2. Again, there's no point in going through the details. So, but I just can just mention that how it comes. This change in direction should be proportional. Change in direction happens only when there is an annihilation of a neighboring particle. So it should be proportional to the number of annihilations taking place divided by the total number of particles present. So those things can be obtained from the particle density decay, and finally we get this value. So after this, as I told you, that there can be some subtleties regarding the updating rules in a Monte Carlo simulation. So we also applied what is called the parallel dynamics. In the parallel dynamics, what happens that you do not update the state of the spins immediately after a single spin flip, but you do, or a single movement of a random walker, but you do it at one go after all the random walkers have been visited. So briefly, it is like this. For the asynchronous case, the other one is called the asynchronous case. In the asynchronous case, suppose this one is being updated, so it will go here, and because there is another walker here, they both will be annihilated in the next step. But in the parallel case, what happens? This may go here, and this may come here, and this may go here. And in the next step, we'll find that P2 and P3 have just switched their positions. And this will be an important point when we are dealing with the parallel dynamics. So I will just mention a few things in this case. We find that the fraction of surviving particles, they show a different behavior. It is log T by T. It is different from what we had obtained in the asynchronous case. And in the, if we take this limit epsilon equal to 0.5, then we notice something interesting happening. This is a snapshot taken at for different times. And you see here that what is happening. Here you see that these motions indicate that there are some kind of ballistic motion taking place. But if you look very carefully, then you can see that there are in this case, two particular walkers which are just switching their positions in each time step. So this is something new occurring because of this parallel dynamics, and we call this a dimer. And it is interesting, therefore, to study the properties of the dimers. But again, let me not go through the details of this. Okay, so once again, we can have some kind of analytical estimate of how the dimerization is taking place and so on. But let me skip through that and move over to another variation of the model, in which we do not have attractive walkers, but we have repulsive walkers. So in this case, epsilon is taken to be a negative quantity. So in this case, immediately you can see that there will be repulsion. So the particles are going to be more long-lived. Okay, because they can kill each other only if they come very close. Otherwise, they cannot annihilate each other. So because there is repulsion, they are not able to kill each other. So there are lots of particles left in the system, be it asynchronous or be it parallel, does not matter much. Okay, so therefore, I have just given you a summary of the results which we obtained for this case. We find that particle decay varies as 1 over log T. There is some controversy over the exact variation. So we initially claimed in one paper that it is log T to the power B, but then the referee, who is most probably this guy, who had a published paper after this paper was published, and there he had done some calculations to show that the variation should be like this, and so referee insisted that you try this, but actually both these are fit the data quite nicely. So we have mentioned both of these, and this was already published by the time, but for the other paper we tried this thing and it also fits and so on. And then persistence probability is completely different. It no longer shows any kind of power law behavior. It has this type of a behavior, e to the power, it is a stressed exponential behavior. These probability distributions are also quite different. They are Gaussian, And but interestingly, the scaling variable is not x by t to the power half, but x by t to the power nu, where the value of nu actually decreases with epsilon and approaches a value 0.25 for epsilon equal to minus 0.5. And this is a result consistent with the case of recursive random walkers, where one gets this kind of variation that the x varies as t to the power 0.25. So that also is consistent, this result. And in the parallel case also we get similar result, only there is a discontinuity at epsilon equal to minus 0.5. On the other hand, these two other variables which we had studied, st and d tau, they behave in the same manner. So I'm just going to give you a gist here about the leading order time and epsilon dependence of rho t, the bulk properties only, not all the properties, just to summarize how they are different. So you see, for epsilon equal to 0, asynchronous and parallel give the same result. For epsilon greater than 0, rho t is different, that is t inverse here, and log t by t. As I told you, for epsilon greater than 0, they will be different. But for negative values of epsilon, they are probably same, and that goes also for the persistence behavior of these two cases. So after this, actually not after this, parallelly, we were doing another thing. Pratik was actually looking at this thing. Actually, this name is not quite correct. We actually studied both the attractive and the repulsive biased walk in 2 dimensions, and using parallel genomics. So Pratik studied this on square lattices, and here the random walkers are on a square lattice, and they can go to here. The probability to go towards the nearest neighbor is taken as epsilon. Sorry for the change in notation. And epsilon here varies between 0 and 1. So if epsilon is 0.25, then you simply have the diffusive point, because here the probability of going to any neighboring site is just 1/4, and epsilon equal to 1 and 0 are extreme positive and negative bias to represent these two cases. So there are some known results for the diffusive walk. For example, the density of particles rho t behave like this. Persistence probability for the parallel dynamics behaves like t to the power minus theta, where theta is equal to half. And of course, dimers are present in this case also. The dimers, as I told you, are basically they are two particles which are just interchanging their positions at every step, and so on. So the thing is that in 1 dimension, we obtain the result that dimers are present only for the extreme positive bias case for the parallel dynamics, but here we will see something different. So as usual, first we will see how rho t behaves. So rho t for epsilon less than 0.25 actually does not attain a saturation value, and we estimate, try this, attempt this fitting that rho t is rho infinity plus some power law fitting here, and then we obtain that this rho infinity actually shows a power law behavior like this, where beta is very close to 2. Okay. And epsilon c is nothing but the purely diffusive point. So we also made another estimate or analysis in which we just took the value of rho at the maximum value of iteration time up to which the Monte Carlo simulation was done. And then we plotted it, and then we tried the scaling collapse, and we found that L square rho T max actually shows a nice collapse with epsilon C minus epsilon L. And here also this is a quadratic variation. So we get back this result that rho T max will vary as epsilon C minus epsilon square, because this L square is going to cancel out as long as we are, this region represents epsilon C greater than epsilon. Okay, and therefore we find that this important result that all particles are not getting decayed if we are beyond this point, if we are below this point, epsilon equal to 0.25. On the other hand, when epsilon is greater than 0.25, we have another interesting quantity. Persistence behavior is just also is different for these 3 regions. Let me skip this. And let me focus on the results for the dimer. As I told you, dimers, here we have shown it pictorially. For small values of epsilon, we are not having any dimers at large times. For epsilon equal to 0.5, we see that there is one dimer. I hope you can see this. There is one dimer. Now this is going to be permanently there because there is no other particle to react with. So they are going to keep on switching positions on till infinity. And so we say that there is a permanent dimer here. For epsilon equal to 1, such permanent dimers will increase in number. As you can see that there are lots in this case. So we made a quantitative study here. And this is the number of dimer per site in this case. And we find that with time, of course, it gets decreased. But for epsilon equal to 1, it attains a finite value. For other values of epsilon also, it has non-zero values. But of course, for epsilon equal to 0, it goes to 0, very close to 0. It is very small. So epsilon equal to 0, it is actually small, 0. So I've almost reached the end, and then we obtain these types of variations. Epsilon equal to 1, of course, is different, and the number of dimers is very large here. But otherwise, the number of dimers can be also shown to be really to obey this kind of a power law variation, where we get a new exponent like this. So finally, it is claimed that there is a kind of phase transition happening at this point epsilon equal to 0.25. Below that, we have a non-zero number of particles. Above that, we have zero number of particles, not non-zero number of particles, because dimers will contribute to the number of particles, but we have a non-zero number of dimers. And here we don't have any dimers. So with that, that is the last slide. And here we have some concluding remarks. These are just repetitions of what I mentioned during the talk, so I'm not repeating it right now. Just a summary. And because there's no time, and thank you very much for your kind attention.
Thank you very much, Professor Shen.
Yeah, I just overshoot the time a little bit, I think.
No, it's
Sorry
okay.
for that.
It's all right.
I had to go fast, I know, but I think I have been able to convey the main points.
Yeah.
Details,
Yes,
if someone
right.
wants to know, of course, we can discuss later.
Now the talk is open for discussion. If there is any question, please, you can just unmute and ask, or you can type in the chat box.
Yeah, they can raise the hand also.
Or can raise a hand, sure. Whichever is.
Hello, ma'am. This is Suprabhat from SRM University.
Yeah, good afternoon. Yeah.
Nice talk. So actually,
Thank you.
So you talked about that mean field dynamics. Can you hear me clearly?
Initially, right? Yes.
Yeah. So, and you talked about that mean field limit. The rho t goes as 1 by t.
Right.
Decays as 1 by t.
Right.
So I was wondering whether that is on lattice, or it is like it is valid for in continuum space.
No. It is just a continuum equation. You have time continuous there, and you are talking in terms of densities. That is the reason. You are not talking in terms of individual particles. So it is a continuum.
No, I was thinking of, suppose your model is specifically on lattice, right?
Right.
Particles are moving lattice, so it is valid in like if you have 2 dimension and if you are moving randomly in any direction in continuum, is it valid there too?
Yeah, you just have to take a lattice constant going to 0.
Okay. But
the lattice constant is not taking in any role here. It's not having any role. So one expects the same results to be valid.
Okay. Thank you.
Siddhartha was saying something, or he's there just because?
No.
So he's their panelist. Hello, Siddhartha.
Hi. Yes, I'm here. Yeah, nice talk. Thank you.
Thank you.
But I'm an experimental condensed matter physicist. So yeah, it's very nice talk. Finally.
Yeah, I know that it was completely theoretical, but it has application.
Yeah. Yes. Definitely.
The estimates that you showed also towards the end, when you mentioned that, I think the direction changes, you said the number of particles divided by
The number of annihilations.
Number of annihilations.
You
But
see, about,
yeah.
so actually that was applicable only for the case of 0.5, because if there is no annihilation, then it will always deterministically go towards the next, the nearest neighbor, and there will be no change in direction if there is no annihilation. But because it doesn't have any diffusive component. The diffusive component comes if you have an epsilon which is not equal to 0.5. So the moment, so that discussion is for 0.5 only, and for that particular case, if you need to have a change in direction, there has to be an annihilation of a neighboring particle. Because if your neighboring particle is getting annihilated, then it may happen that that was the nearest particle. So that, say it was on the right, but there is no particle on the right now, close particle. So the closest particle now lies on the left. So therefore it changes direction. So for 0.5, that the probability of change of direction depends on the number of annihilations, and we are scaling by the total number of surviving particles. So that's why you divide by that.
But that sounds like very much a mean field estimation. But
of course, yes.
But it works for your lattice.
It works for our case, right?
Even for very low dimensions.
Right. See, you see, T inverse is also there in the mean field case.
Yeah,
right,
yeah.
but the reasons are completely different. So if you just think a bit that what is happening here, that if you take that limit 0.5, then essentially it is a rich gets richer type of thing going on. The largest domain will go on picking up members, so that ultimately it will just expand the whole thing within linearly in time. That's fine. Just doing a walk straight like a ballistic walk. But it is, the mean field result is not related. So as I told you, the exponents may be same, but the basic phenomena may be quite different.
And one last question from my side.
Yes, of course.
So of course you studied persistence here, and you also mentioned SIR model at the beginning. I don't really know if SIR model can map to some kind of spin dynamics or not.
No, it maps to percolation model, of course. It maps to percolation model.
Is it possible to calculate something like a persistence in SIR? Because that would just mean that how long a person stays uninfected during a pandemic.
Of course, you can study it what kind of, in a mean field model, I don't think.
Mean field would give you nothing.
No, because persistence means you are looking at the individual behavior.
But in lattice, I don't know. It might be interesting. How long a person can stay uninfected. Exactly. So one survives the first wave, the second wave now gets infected in the third.
Oh, great! You already formulated a problem.
No, that's a problem I faced. I think you got infected in the third also. So.
Right. Many people actually.
No, Siddhartha got infected in the second. Ranjit,
but it will not be so simple as SIR, because many people got infected twice. Even thrice.
Okay, anyone else? Anything else? If not, then thanks to the speaker again for a wonderful talk.
Thank you.
And over to you, Ranjitda.
Yeah, actually, Amit is actually the moderator, but his laptop
Amit's laptop got,
suddenly,
I see.
Suddenly it's a technical fault. Anyway, so on his behalf, it's really wonderful and very good informative talk, and particularly very deep study. And also the first half was really understandable to the layman also. So I hope our students and others also got really motivated by such very organized way how we can give a talk. So this is very important for us to learn from the students' point of view. So thank you, Professor Sen, and this is really very good and very clear actually. And now I wish to thanks Dr. Somojyoti, who organized and invited you the 6th Eminent Guest Lecture Series, which we started almost 7-8 months back from Department of Physics. And we will go for more like this will be our department main lecture series for long run. But of course, as it is as I told that already, as it is online, so we can do bi-monthly, but later maybe in 6 month or 3 month one. So, so I request anytime, madam, you to visit in our university through any other way, like maybe as an external member or any other things.
Yeah,
So,
I'd love to. Actually, thank you very much. So I feel flattered by your words, really. I would also like to mention one thing, that I think it's really after a long time I'm giving a talk in which Shobhajyoti's name doesn't feature, because I have been collaborating with Shobh. Only I think quantum random walk I have not worked with you, but for all other types of problems. So anyway, Shobh has compensated for that. Another Vishash.
Yeah, so and thanks to ITKM who supported a lot of webinars and all our webinar series in the university. They are really a very dynamic team. And Dr. Amit, who is the in charge of this webinar series from our Department of Physics, and all our faculty members and students, and from outside participants also, we thank. And with this, I think we can close the session. So thank you, Professor Singh.
Thank you. Thank you so much.
Thank you.
Okay.
Thank you. See you soon.
See you. Yeah.
Sooner than you think.
Okay, then. Bye.
Thank you.